Hello, I'm Shadwin.
I'm Shaiki. I'm Hui.
I'm Joey.
I'm Madeline.
Today we will be discussing about the production of methanol from syngas.
The title of our assignment is the production of methanol from syngas. So basically, what is syngas? Syngas is a synthesis gas from natural gas, which mainly composed by carbon dioxide, carbon monoxide, and also hydrogen, with a little amount of water, nitrogen, and methanol. So the objective of our project is to define the proper operating conditions for the simulation of methanol from the synthesis gas. So basically, here are the three main reactions that take place in the CSTR reactor. So for the first two reactions is the carbon monoxide and carbon dioxide hydrogenation to methanol. For the third reaction is the water gas shift reaction, which the carbon monoxide will react with the water to produce carbon dioxide and go back to the carbon dioxide hydrogenation. For the first two reactions, it is an endothermic reaction, which usually a low temperature and high pressure is favorable. And for the water gas shift reaction is the exothermic reaction.
Before we start to the unit C, now we will proceed to the information we need to key in. So we need to follow the 5 steps before we go to the unit C. So for the first one, we need to key in the component need, which is carbon dioxide, carbon monoxide, water, methane, hydrogenation, and the methanol. And the second stage is about the free package. In our assignment, we choose SRK as our free package. And the third one is the reaction stage. There are 3 equations we need to key in, such as the carbon dioxide hydrogenation, carbon monoxide hydrogenation, and the WGS. We need to key in the stoichiometry and the forward and reverse reaction. And then the fourth factor is the global reaction stage we need to add. And the last one stage is about the free package we also need to remember to add. So now we can process to the unit C to look for our process flow like that. So here you can see this the syngas. Yeah, we key in all the composition we need in the syngas, and then we put into the mixer. And this one is the recycle one. Yeah, in the beginning we just assume the information we need, and then after that we go to one of the cooler, and then we cool the temperature until 10 degrees Celsius. Yeah, and then we go into the CSTR reactor. Here you can see we have success to convert the 3 reactions. This is the result. Yeah, and then we also can see the composition. Yeah, and then 2 of the outlet we combine into a mixer, and then we put a heater to heat the temperature until 100 degrees Celsius before enter the separator. We use the separator because we have 2 phases, which is the vapor phase and the liquid phase. For the vapor phase, we also add 1 more T to remove the purge. And then another, before that, we also need to set the flow ratio for the purge, which is 0, and another outlet is 1. And then we use the compressor to compress the pressure until 4000 kPa to recycle back as our feed. So another stream liquid from the separator is now connected to the distillation column. Before we use the distillation column, we need to get all the information we need, such as the, yeah, you can see, such as the number of stages. From this shortcut column, we know that the number of stages is 10, and the best in the stage is 8, and the pressure condenser is 1000 kPa, and pressure reparator is 1015 kPa. Another information needed is such as the, this one. Reflux ratio is the 3.34. And the distillation rate is 1.72 kg mole per hour, and another one is the ventilation rate with 26.2 kg mole per hour. And then we use the distillation column to replace the shock cap column. From the distillation column, we get the methanol from the ventilation, and then we cool the methanol to become the liquid methanol until the negative 100 degrees Celsius, because the melting point of the methanol is negative 97.6 degrees Celsius, and then we put a storage to keep all our liquid methanol storage. Okay, so in the end, we success to get our methanol purity in the liquid methanol storage is 0.9769, and the molar flow rate is the 25.78 kg/mol per hour, and the temperature is negative 100 degrees Celsius. And then the total heat demand in our PFD is 1.076 E plus 008 kg per hour. Okay, this is our PFD of production of methanol.
I'll be talking about result and discussion for our simulation. Once we have done with our simulation, we found out that there is 4 parameters which affects our purity of methanol. I'm going to discuss the first parameters, which is feed state to distillation on purity of methanol. In our distillation column, we have 10 stages. The numbering starts from top to bottom, and we found out that as the stages increases, the purity increase, but it starts to be a constant at the 8th stage. So we concluded here that the 8th stage will give us the highest purity of methanol. The second parameter I'll be discussing is about variation of reactor feed temperature on conversion of CO2, CO and methanol production rate. From the graph, we can conclude that as the feed temperature increases, the conversion of CO2 and CO will decrease, whereas the temperature that we tested from 10 degrees Celsius to 50 degrees Celsius, the methanol production rate remains as constant.
Alright, so the third point that we're talking about is variation of reactor feed pressure on the conversion of carbon dioxide, carbon monoxide, as well as methanol production rate. So as you can see from the graph, as the feed increase, which is the reactor feed pressure, the conversion of carbon dioxide and carbon monoxide will decrease as well, whereas the methanol production rate will decrease as you increase the reactor feed pressure. Alright, so the last point I'll be talking about is the separator feed temperature on purity of methanol. In the graph, you can tell that when the feed temperature increases, the purity of methanol will also increase. So basically, to have the highest purity of methanol, you will need to use the highest temperature. But with that said, the higher temperature that you use will also incur more cost because you require more energy. So the selection of your temperature should be solely based upon the requirement of your production.
I'll be talking about the recommendation for our simulation process. The first recommendation is methanol purity. To increase the purity of methanol, we can increase the number of distillation column used. In our original process, we used one distillation column which only separates water and methanol without considering small traces of gases such as carbon dioxide and carbon monoxide. To increase the purity of methanol, we can use more than one distillation column, which will come to our second recommendation, which is production cost. As more distillation column is used in a process, it will increase the production cost of a plant. So ultimately, this depends on the client requirement of methanol. If he requires high purity, the more number of distillation columns should be used, but your production cost will increase as the number of distillation column increases.
Okay, so the third recommendation would be about the separation ratio. So our recommendation would be to add a recycle loop which contains a methanol reactor, a separator and another cooler. So basically how this works is we will condense the vapor phase coming out from the separator and then send it back into another separator to ensure that the separation ratio is high and recycle it back into the first separator. So this process will increase the separation separation ratio before it is sent into the distillation column. Alright, so the last recommendation for today would be productivity. Basically, from mass balance, you can tell that your mass flow in will be equivalent to your mass flow out. So to increase your productivity, the obvious way is to increase your feed as well. But productivity in itself is also linked to purity as well as separation ratio. So there is no point to increase your productivity if your purity is not high. So these two factors will also link to each other.
In the conclusion, these are the optimum conditions for the parameters in the production of methanol. Firstly, the optimum feed stage is at the 8th stage, where the purity of methanol increases in higher feed stage and reach constant at 8th stage onwards, and as the highest composition of methanol is achieved at this stage. So the second one is the optimum reactor feed temperature, which is at 10 degrees Celsius. The conversions of both CO and CO2 decreases with an increasing reactor feed temperature. So the max conversions achieved are 0.99 and 0.43 respectively, and the methanol production rate is constant. The third one is the optimum reactor feed pressure at 4000 kPa. So at this pressure, the conversion of CO and CO2 are the highest at 0.4 and 0.91 respectively, and the methanol production rate is at 26.05 kg mole per hour. So the last one is the optimum separator feed temperature at 100 degrees Celsius. So this temperature is the ideal temperature for the separator to achieve highest purity of methanol, which is at 97.69%. However, higher energy is required at higher temperature, and thus the operational cost